Hi everybody, and today I'm going to talk about Gate 2023 analog questions. Okay, they have been asked in electrical engineering as well as in instrumentation branch. Okay, so hi everyone, good evening, right? So we'll take first questions, and you guys also have to try from your side, and you have to learn the way we are going to solve this question, right? Because all the questions what we have been talking in the classroom, right, had been appeared in the gate examination this year, right? So let's take first question. The very first question. This was asked in instrumentation branch, right? So we have to try this question. So let the moment you see the question on your screen, you need to go through very properly, right? Okay. So what is given here? The figure below shows a feedback amplifier constructed using NMOS transistor. Okay. Assume that mu ux equal to 1 milliampere per V square, right? So they have given mu ux and Vt, okay? They have given threshold voltage is 1 volt, WIL ratio is 2 volt. The bias voltage at drain terminal they have given. It means they have given this is the drain terminal, this is the gate, drain, and this is source, right? Okay. So they have given here Vd. Vd is given as what? 4 volt, right? The capacitor C infinite offers zero impedance at the signal frequency. So we have to find the gain here. V out by V in. Okay. What we have to find? We have to find the gain. So first of all, you have to identify that what kind of configuration they have given here. So see here, you are applying input at gate terminal and you are taking output at source terminal, right? So this is common, what? Common drain amplifier, right? You can say this is common drain amplifier. This is first, observation you have to make. CD, common drain amplifier. Okay, how do we identify that this is common drain amplifier? Because you are applying input at gate and you are taking output at source, right? So this drain terminal is common. Okay, this is first, and common drain amplifier. Okay, from the very basic you must know that this behaves like a voltage control voltage source. Okay, so it's okay if it is a voltage control voltage source, so its gain, should be less than or equal to, you can say, it should be approximately equal to 1 or less than 1. Okay, it should not be greater than 1. Okay, that is what you have to understand. Perfect. So now what you have to do here is they have given these parameters mu n ux vt and wyl, and this is n channel MOSFET they have given. Okay, this is n channel MOSFET. Okay, so what you have to do here is you have to you have to understand that this amplifier is in saturation. Okay, MOSFET we have like an amplifier only when it will be in saturation. Okay, so if this Vd is given, so first of all you can do the DC analysis. Okay, while doing DC analysis, what you can do, you can remove this capacitor. Okay, these capacitor you can remove by open circuit, right? So you can find this VG here, right? Why we are finding VG, and you can also find this VS here. Okay, so VS can be directly calculated. How we will calculate VS? Let me tell you here. So you can draw the circuit again. This is the circuit now. Okay, for DC analysis you can draw, right? And because these resistor what we are using here is these R1 and R2, they are used for biasing purpose. That's it. Okay, other than, while calculating the gain, they will not come into picture, right? Only while finding these potentials at the gate node, gate terminal and the source terminal. Okay, we are using this. Okay, because this is a 5 volt, okay, supply, so you can apply the voltage division. This is 5 volt, right? So this is 200 and this is 300, okay, in kilo, right? This is given in kilo. Now can you determine what is Vg here? So Vg you will be getting here is what, by voltage division rule. So 5 into 300 by 500, right? So these two zeros get cancelled, 5 5. So this is 3 volt, okay, at Vg. You can say Vg will be equal to 3 volt, right? And we know that this is 1 k ohm. They have given the potential at drain terminal, that is you see 4 volt. So, and this is what 5 volts. So you can find the drain current ID. Okay, you don't have to use the equation for the drain current in the saturation region. That 1 inch long equation is there. So you can directly find ID. ID is going to be what? 5 minus 4 upon 1K, which is going to be 1 milliampere, right? Now this 1 milliampere will flow through this 1 kilo ohm resistor, which is given at RS, right? So this is 1 kilo ohm resistor. Here current is flowing 1 milliampere. Okay, because you know that gate current, gate current will be zero. Current through gate terminal will be zero. So drain current will be flowing through RS as well. Okay. Now you can find the potential difference because potential across this RS, right? RS. Okay. Because 1 milli into 1K, it will be 1 volt, right? So you can say that the potential at source terminal, that is Vs, is going to be 1 volt, right? Now you can simply find VGS. What is VGS? VGS is going to be VG minus Vs, which is 3 minus 1, okay? And this is going to be 2 volt, right? And you know that if VGS is greater than VT, then only this MOSFET will function, okay? It will work, right? So VGS equal to what? 2 volt. We have got this. Now you can now do the AC analysis, okay? So this you have to do before you try to calculate the gain of the transistor. Okay, now I will tell you how to find the gain of the transistor, right? So now you can forget about these resistance you can forget about because they are connected for biasing purpose, right? Okay, so we will forget that register, right? Now what we will do for AC analysis, we call it AC analysis, right? Or small signal analysis also we call. So this is just I'm telling just to understand because you guys are naive. Okay, so you see here. Now what you have to do while doing DC, sorry, AC analysis, okay, this is V naught. You have to short circuit the capacitances, okay, because AC analysis means at low frequency you have to short circuit the capacitance. So here, whatever capacitance are present here, you see this will be short circuited. Okay, now you are applying the signal directly. Okay, this is RS. RS is 1 kilo ohm. Okay, and this is you see this is given as 1K, and now your VDD will be grounded, right? This is grounded, and you see here this is R1. Okay, why I'm telling this R1 will not come into picture, now you will understand. Okay, so see R1 and R2 will be, they are grounded here as well and here as well. So you can take R1, okay, you can take R1 like this, you can connect R1 from, you can remove R1 from here, and you can connect like this also, right? And now you are applying the voltage signal, right? That is input Vs. Okay, that is input V in, you say, right? So it is very easy now, right? So this is V in, and this is R1. So you see here these resistances are used for biasing purpose because you are applying input directly across these resistors. You can say this input is here, right, directly. Okay, so you can also remove these resistances. Just I have shown you so that you should understand, right? So you can remove now. Okay. So now your input is connected directly to the MOSFET, right? So let me draw properly. Now, what you can do now is, as it is a common drain, right? So common drain amplifier. So how can you write the gain? I will discuss in detail how to write the gain and all, but you should know that you are applying input at gate terminal, okay, and you are taking output at source terminal, right? So it is a common drain amplifier. So you should know that the gain is basically the ratio of, okay, that you have to understand. The gain is basically the ratio of out resistance seen from output node to the ground, okay, resistance seen from output node to ground, okay, that you have to understand, and upon what will be here, upon resistance seen from the source terminal, okay, upon resistance seen from the source terminal, resistance seen from terminal. This concept you have to remember always, just so that you can write the gain expression directly. So gain will be equal to, you see, if you take this is output node and you see from here to the ground, what is the resistance, guys? That is Rs, okay, upon. Now you have to see the resistance from this source terminal. So it will be 1 by Gm from the source, and if you see from here, so this Rs is coming in series, so you can say the resistance will be 1 by Gm plus Rs. Okay. So when we will draw a small signal model, during our classroom, right? So what we will do, we'll get, when you see the resistance from the source terminal, you will always get 1 by Gm, okay? And when you are looking from, when the source is degenerated here, source resistance is present, means we call it source degenerated, okay? And this will be have like a feedback, because in the question also they have mentioned the feedback amplifier, okay? Why they have mentioned feedback amplifier? Because this Rs is present. Okay, you see there is no connection from out, like if you see here, okay, so output input you are not able to see anything, right? But you see here this Rs is present, and this Rs is we having like a feedback register, right? So you can say this will be 1 by Gm plus Rs, right? So this is the concept which you have to use always, okay? For any kind of amplifier, be it BJT or MOSFET, okay, or any kind of configuration. Understand, guys? So AB will be what? AB will be Gm Rs upon 1 plus Gm Rs. So most of the people will say that mug up this this expression. Needless to mug up, you should know how to determine, right? Now you have to only calculate Gm because Rs is present, okay? And you can also do sanity check here. If you want to do sanity check, you can do, right? If Rs is not present, then what will happen? If Rs is not present, then what will happen? Rs means it is 0 and it is 0 also, right? So it becomes 0, okay? So Rs should be present, okay? If you are trying to find the output at, okay, measuring the output at source terminal, right? Okay. So, and if suppose Gm is Gm Rs is far greater than 1, so you can say that this gain will be approximately equal to 1, right? As it is a common drain amplifier and it should be have like a voltage buffer, as I said in the beginning, right? So, but here you have to calculate Gm. So how to calculate Gm, guys? Okay, how to calculate Gm? That is what the question is now, right? So we'll calculate Gm. So as we know that what is Gm? Gm is basically mu1 Cux W by L VGS minus VT. Okay, how to get this Gm? You should know the expression for ID, right? Current equation for saturation, that is 1 by 2 mu1 Cux W by L, right? VGS minus VT whole square. Understood? So you can differentiate this with respect to VGS, okay? So dou ID by dou VGS will be equal to mu1 Cux W by L, VGS minus VT. And this is the GM of the transistor, right? This is the GM of the transistor, okay? Now you can plug the value. So mu1 Cux is given here in the question directly, so 1 milliampere, okay? And this is 2, right? So you can say this is 2 milli, 2 milli means 2 into, minus 3, okay? uh, okay. Now what is W? W by L is also we have taken into consideration, and VGS is what, guys? VGS is 2, right? So 2 minus 1 is 1, so it is 2 milli Siemens we have got. Now you can easily plug here. So AB will be what? You calculate from here. So I'm just writing here AB is going to be Gm is 2 milli and Rs is 1 kilo. So it will cancel, milli kilo cancel, right? 1 plus 2. It is 2 by 3. What is 2 by 3? Can you calculate? 2 by 3 is going to be 0.66. Okay. You will get 0.66, right? 2 by 3 is basically what? 0.667. Right? You can write like this, 666. Okay. So you can approximate like 0.67. Understood? So answer for this question will be what? Answer for this question will be, yeah, Amit, correct. So answer up to rounded up to 2 decimal you have to write. So you can say 0.66, okay, or 0.67 is also correct. Understood? So this question can be done within you can say 40 seconds, right? I am explaining you, that's why we are taking time, otherwise you can do easily, okay? Because once you will complete your analog class, so the way I'm doing, you will quickly do, right? Because whatever information is given, you don't have to call like DC analysis separately and AC analysis separately. Depending upon the gain expression, see, we need this GM, okay? We need this GM. How to evaluate GM? We need VGS, right? So we only know VS potential here, because of ID we know this VS, but we don't know VG. So we need to find VG, okay, by doing DC analysis, right? So while doing DC analysis, you have to remove these capacitances, okay, by open circuit, okay. Like signal and DC should not come into picture that time, right? Only DC. And by applying voltage division rule, you can get VG here, okay, at this terminal, and VG minus VS is VGS, okay, so that you can evaluate GM of the transistor, right? Okay, yeah, Amit, correct. 0.67 you can say, right? It is the correct answer according to the key as well. Yeah. Perfect. So this is the rule, and you see, guys, we are taking positive gain. Okay, there is no phase shift, right? See, whenever there will be common source amplifier, always keep in mind, whenever you are applying, whenever you are applying input at gate and you are measuring output at drain, it means that is common source amplifier. So there will be a 180-degree phase shift as well. Okay, so there should be a minus sign, but in this case, in case of common drain and in case of common you can say common gate, right? Because common gate means what, you will apply input at source and you will take output at drain, right? So there will not be 180-degree phase shift, understand? It will be positive gain, so answer will be 0 point. You see here, this answer should be less than 1 or exactly 1, right? So you see what answer we are getting, it is less than 1, so it is correct. Okay, let's move to this question. So this was the question again, asked in the gate examination. So again, this question was from our, from our notes only, whatever we have taught, whatever concept we have discussed in the classroom. So in the class, in the circuit shown here, assuming op amp is ideal, see, the moment they have given op amp is ideal, so your life is very simple. Okay, your life is very, very simple. Okay, you don't have to worry about anything. The value of output voltage V naught we have to find and round it up to 1 decimal places. So easy guy, you can try this question, and Dharika and everybody. Okay. So if you know like a prior how to do that. Okay. See, as we know that if op amp is ideal, okay, if op amp is ideal and input is connected, you can see here, right? Input is connected at the positive terminal here, you can say. And if op amp is ideal means op amp will not accept any current. These are the assumptions we make, okay, while solving the op amp, okay, so that you can solve the op amp easily, right? So op amp should not accept any current if op amp is ideal, okay, there should not be any current, okay, because uh, so these two resistances are in series, you can understand. You see, when there is no current, so whatever current is flowing here, the same current will flow. And if the same current is flowing, means resistances are in series. You can say like this. This is 3R and this is 3R and this is plus V naught, right? Okay. So you see here, guys, what will be potential across 3R? Tell me, because these are the two same resistor. Okay. So if you apply the voltage division, so equal voltage will be will be across 3R and 3R, right? So you can say V naught by 2. So this voltage we are measuring across this. This is V naught by 2. Directly you can apply this. Okay. Voltage division is applicable. You don't have to apply KCL here, right? Why to apply KCL? You will get the same result, right? If you apply KCL also, you will get the same result. Understand? So that is first assumption we have made. That is, if op amp is ideal, there should not be any current. Okay. And second assumption is the potential at negative terminal. Okay, and the potential at positive terminal should be same. We call it V minus should be equal to V plus. We call this condition as the virtual short concept. Okay, or virtual short condition, right? We are thinking that, okay, so that you can analyze the op amp circuit, right? Because at this node, if you think that you can apply the KCL, you can't apply because you don't know the current output current of the op amp, right? So you might know this current, okay, all the current you know, but at this node you don't know the current, right? So you can't apply KCL at this node, okay, at the output node, always keep in mind. But you can apply the node here, KCL here, you can apply KCL here, right? But you can't apply KCL here. There is a reason. Okay, so sometimes KCL, if you try to apply KCL, means there will be a problem. Okay. So the potential at negative terminal should be equal to potential at positive. So you can say that this is a positive terminal, right? So you can say the voltage across this will be, V naught by 2. So you can say here, I'm telling, right? Whatever potential is here, the same potential will be here. Now, this is a problem of network analysis, right? Because the potential here is V naught, right? The potential here is V naught, and this is kind of a, you can say, star network, R. Okay, so we have different techniques to solve this kind of a question. Okay, so what you can do here is you can consider that see, if you know these potentials, you can find the current here I. Okay, so I will be what? I will be 1 minus V naught by 2. Okay, so you can find this I will be what? 1 minus V naught by 2 upon 3R, right? If you don't want to use star to data conversion, you can apply simply KCL. Okay, I hope this makes sense. I equal to 1 minus V naught by 3R. Okay. And if you consider Vx here, you can apply one KCL at this point as well. So KCL is going to be applied here, right? So you consider this current is going here like this and this. Okay. So just I am applying KCL to the next page. So you see here, it will be Vx. Okay. Vx minus V naught by 2 by R. Okay. Plus Vx by R, okay, plus Vx minus V naught by R, right? This is equal to 0 because we are applying nodal analysis, okay? Correct. So now what you can do, you know that denominator is going to be same here, so you just add 1, 2, 3, so 3 Vx and V naught, and V naught by 2 minus V naught, okay, that will be minus 3 V naught by 2. What? Equal to 0, right? So what you have got here is Vx equal to V naught by 2. Understood, everybody? Is it correct? Okay. So you see here, we are just simply applying nodal analysis. That's it. If you don't know how to convert, you can solve this any network. There are different methods. Okay, method of doing solving the question. But here, what we are doing, simply applying KCL, right? Simply, and there is no. You can also apply other. You can also apply some theorem as well. But why to complicate? Okay, so this is what the situation is. So Vx here is what? V naught by 2, right? And as you can see, this I, if you find this current through this, right? So this I will be in terms of Vx if you calculate, okay? So what is current through this R if you evaluate? So I will be what? I is going to be the same, I is going to be this, okay? And you can say I will be equal to V naught by 2 minus Vx, okay, upon R. Okay, if you take the direction like this, okay, so this is V naught by 2 minus Vx by R, right? Now these two currents are same. You see, this current and this current is same. Am I correct? One current is coming and one current is going, so you are applying incoming equal to outgoing. So 1 minus V naught by 2, you just equate these two equations, right? So just I'm going to equate here. So 1 minus V naught by 2 upon 3R equal to, okay, 1 minus V naught by 2 upon 3R equal to V naught by 2 minus Vx by R. Why I am doing so? So that we can express this Vx in terms of V naught, and my answer is V naught only, right? So R and all you can cancel here, and then what will happen here? This is it will be 1 minus V naught by 2 equal to this 3, you can multiply that side, 3 naught V naught by 2 minus 3 Vx. Yeah. Okay. Now, so what you can do now is you can take this guy 1 minus V naught by 2 by 3R. Yes. equal to V naught minus Vx. Okay, so R are gone, and this 3 we have taken this side. So yes, it is okay. So now you can take 1 plus 3 Vx equal to this V naught. Okay, so 3 V naught by 2 minus V naught by 2. So what you are getting here is 1 plus 3 Vx equal to V naught, right? So 3 Vx equal to what? V naught minus 1. So Vx equal to what? It will be V naught minus 1 by 3, right? So you know already this, so you just plug back this guy here. Okay. So this is V naught minus 1 by 3 equal to V naught by 2, right? So now you can cross multiply 2 V naught minus 2 equal to 3 V naught, right? So how much we are getting here? uh, minus 2 equal to 3 V naught minus 2 V naught, right? So yeah, but we have to find the value of output voltage V naught, right? So yes, so what will be there? This is V naught, so it is coming out to be, I believe, it is coming out to be how much? 2 V naught, yes. Somewhere we have done, I guess, yeah. So this is V naught minus 1 by 2. 1 minute. Yes, 1 plus 3 Vx equal to 2 V naught. Yes, it should be 2 V naught. No, see, 3 V naught minus V naught by 2, right? So you can say it will be 2 V naught by 2, right? It will be cancelling 1. Yes, you have to take care of this. Uh, so you are talking about, okay, let me check. Acha, ha, this, yeah, it is correct. Yes, yeah, it is correct. Yeah, it should be plus here, so it will be 2 V naught. Perfect. Okay, so yes, right? So you see here, this is going to be 3 Vx equal to 2 V naught. Okay, that's why the answer is coming out to minus 2, right? But answer should be 2, I believe. So this is minus 1. So Vx equal to 2 V naught minus 1 by 3. Okay. So let me do again this. So this is going to be 2 V naught minus 1 by 3 equal to V naught by 2, right? So 4 V naught minus 2 equal to 3 V naught. So this is V naught equal to 2. Okay. So answer will be 2 V naught. Yes, 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 Amit. Yeah. Thank you so much. Okay. To yeah, because this was minus V naught. So if you're taking this side, so it should be plus V naught. Yes. Perfect. So answer will be for this question 2, right? So the answer for this question is 2 volt. So what you can do, guys, here, there are various method of analyzing this network. Okay, because this is the start network, so you can also convert into delta, and then you can go, because delta will be what? 3R, because all resistances are same, R. So delta will be having 3R resistance. Okay, so this question was again very simple question. So first question was amplifier one, and this is the op-amp one, right? So in op-amp one, you don't have to commit any kind of mistake here, right? Like, we have missed this minus V naught, and we are taking this guy this side, so it should be plus V naught. Otherwise, you will get minus 2 as her answer, right? So answer for this question is what? 2. Next. And this was one of the very good question, okay? In again in instrumentation branch, you see, the op-amp in the circuits are ideal, okay? The input signal are, okay? So we have got input signal, we have got the DC and the AC, okay? What is this? This is DC and this is AC, right? And Vs2 is again given DC plus AC, right? We have to find the average value of the V naught. So can somebody tell me what is the average value of sinusoidal? Yeah. See, this is linear circuit, okay? Op-amp is a linear circuit, okay? Because op-amp is ideal also here. And what is the average value of sinusoidal? You know that any sinusoidal is given, so average value of sine is always 0. That you have to keep in mind, okay? So what you can do here is, when you are trying to find the average value of output V naught, that output V naught, okay? You can say across this, at this node, okay? They are not asking with respect to the, they are asking at this node. Remember this. Okay, many people think that this is wrong question. Okay, but it is not wrong. Okay, you see, suppose we have got you know this kind of situation. This is suppose this is VA and this is VB. Okay, so anybody can find the potential at this point V naught. Okay, and there will be a ground. Okay, so you can find the potential at this node. How you can find the potential at that node? By applying superposition or simple. If you know VB and VA, and if you know the current flowing through this, you can simply find it. Yeah, so you have to find average value of V naught. So what you have to do, guys? You have to take Vs equal to 3 here. Okay, because DC is going to help you to determine average value. Don't consider this, otherwise entire expression will be complicated. So you have to think directly. And Vs2 will be equal to -2 you take. Okay, just take DC and start analyzing. So as we know that this op amp is ideal, so the potential at this positive terminal and the potential at inverting terminal is going to be same, so it will be 3 volt here and this is -2 volt here. So this 3 volt will come here and this is -2 volt come here, so you can determine the current. Okay, so what is the current flowing through this? That will be what, total 5. I'm just considering the current here, so it will be 3 minus of -2, okay, upon R. Understood? So it will be 5 by R, right? Okay, so as we know that op amp does not accept any current, so no current will flow here through these terminals. Okay, so this current will flow through this. Okay, so what is the voltage drop across this? If 5 by R is flowing, so it will be 5 volt and it is flowing downward, you can see. Okay, and the voltage across this will be what? The voltage across this will be 5 volt only, right? Understood? So you know that this, if this is 3 and if this is 5, so if you're going up, you're going up, right? So it should be 8 volt. Okay, that is straight away you can find out, right? Suppose this was 8 volt, so you're coming down. Coming down means you have to subtract, okay, because plus minus is 6. 8 minus 5, you are getting 3 here, right? And see, it is again, you see, this is -2 and this is plus 8. Okay, so you have to find the voltage at this node, right? So what is the voltage at this node? Okay, see, if you're going up, right, if you're going up, you are getting -2. Okay, and this is 5. So what you have to put here so that you should get -2? Can somebody tell me? Yes. Tell. Yeah, fast. What should be the answer? Amit, you can try. Suppose this is VS, or I have written here VA, it's okay, and this is VB. So what should be VB here? So you can also apply it like this. So this is plus minus, and you're going up like this. Okay, so you can say minus VB minus 5. Okay, and this is -2. Okay, already it is given minus plus. Okay, so you can say that it will be -2 here, so it will be 0. So VB equal to what? -7, right? Okay, VB will be equal to how much? -7. Understood? Yes, please respond if you are not getting this. Okay, so if this is -2, yeah, perfect. So VB should be -7, then only you will get -2 here. Okay, because 5 drop is there now. There is a 5 drop, means yeah. So -2 plus 5 drop. Okay, you are coming down here, so it should be -7 volts, right? Okay, now we have got two potentials, right? This is VB and this is VA. So situation is like this. This is 8 volt and this is -7 volt. Yes. Okay, if calculation is correct, then it will be correct. Okay, remember this. So we can also check this calculation. Okay, so so next, what will be the action? What action we have to perform? You can find the current also. Okay, you can find the current. Okay, so what is the current flowing through this? This is R and this is R, right? So 8 plus 7. Okay, 8 plus 7 by 2R. Okay, so it will be 7.5R, because 15 by 2R you have to do, right? 15 by 2R will be there, okay, because total voltage across this is how much? That is 7 plus, okay, yeah. So yeah, 1 minute. Okay, perfect. So V naught 2 we are getting is this, yeah, perfect, right? So what we can do here is this is the potential here will be the current will be flowing here. That is, let me take this 8 minus of minus 7 by 2R, right? So it is how much? 15 by 2R, that is 7.5 R, right? Now it is direct, okay. You see, what is the potential drop across this? This will be 7.5, okay, volt. Now you have to find this potential, okay, or you can say the potential drop across will be 7.5, okay. So if this is 8 volt, guys, and if it is 7.5 dropping is here, what is the V naught? Yes, what is the value of V naught, guys? You can directly tell. See, if this is 8 volt, if it is 7.5 drop is there, so you are coming down, okay. If you are coming down, so this V naught should be 0.5. Everybody is agree or not? V naught should be 0.5. Yes. So this V naught will be, let me draw here the picture and understand properly, okay. This is the concept you have to use always. This is minus 7 volt. This is R, you have to find V naught, and this is plus 8 volt, and you have got the potential drop across, this is 7.5, okay, and this is 7.5. Yes, if you're coming down, so if it was total voltage is, yeah, perfect. So 8, so it will be zero point 0.5. Okay. So this is how we have to solve this question. So this question again was very simple. So answer will be 0.5 volt. Okay. The average value you are trying to find. Okay. So in the beginning, many people were saying that this question is wrong and all, but this question is not wrong. You see, you have to find the potential at this node. Understood? Don't take ground here until it is given. Don't take ground here, otherwise the, okay, contradiction will be there. Understand? Okay. Now we will solve this question. This question is, this question is based on diode. Okay. All the statements in the circuit shown in the following figure are ideal. Which of the following statement is true? Okay, or true. That is MSQ question. So this question we have to do, we have to do by observation, and here no calculation is needed. Okay, so first of all, what you can do, you just take ground here, okay, and read the option first, what they want, right? So they have given this switch here, right? So when switch is on, there are two conditions. When switch is on, you have to check what is the status of the diode, okay, D1, D2, D3, and when switch is off, okay, means it is open. So D1 and D2 and D3, what will be the status of them, right? Okay. So initially you can consider that the switch is on, right? Initially switch is on, okay, means the, if it is short circuited, right, so this, there will be a voltage 0 volt, right, and this guy is 40. So as we know that from the very basic, if this is a diode, and as we know that if you look from this side, so this is basically the anode terminal, right, and this is the cathode terminal. If you look from this side, okay, so this looks like a K, that's why we are calling it cathode, yeah. This is how we can understand. So this is Vk. So if Va is greater than Vk, then only your diode will conduct. Otherwise, diode will not conduct. That you have to keep in mind. Understood? So in this case, you see this potential at anode is less than the potential at, okay, the moment the switch is closed, right? You can see switch is closed, so 0 volt is there and 0 volt will be. So D3 will be off. Okay, D3 will be off. Off meaning is what? D3 will be reverse bias when diode will be on. That you have to keep in mind. Okay. So if D3 is off, okay, if D3 is off, you see guys, okay, and this guy is what, 20, okay, this is 20 here, understood? And you see, if you consider the potential at this point, okay, so what is the potential? 20 volt here, and here the current 4 ampere is coming, and this potential is given as 10. which one is greater? The potential at this point will be definitely lesser than the potential at this point, that is 20, right? So D2 will not conduct. Okay, so in this situation, you see from the option, when switch S is on, both D1 and D2 conducts. This is wrong. Okay, this is wrong. So here D1 will conduct, certainly it will conduct. Okay, you see, because this is 0 volt here, and this you can say around approximately 10 volt, you can say, or it will be less, some drop will be there. So some potential is there, but greater than 0. So this guy will conduct. So you can say option B will be the right choice for, yeah, Narika. Yes. And now the situation you have to consider like this. This is for first. Okay. Now you take, this is open. Okay. Let me remove this. Now you consider that this guy is open. It means switch is open. Okay. So this will not be correct. Okay. Option A is gone. Right. Now, when switch is open, so what will be the right choice between C and D? You don't have to look now A and B. You have to look for C and D. So this is open, right? So if this is open, then what will happen? This guy, if it is grounded, so it will be 20 volt, right? So definitely D2 will be off. Okay. If if it is open, so it is not going to affect your D2. D2 will be remained off. Okay. Understood, everybody? D2 will be off or not? Think about this. D2 will be on or off? Yes. Yeah. Think and let me know. Yes. Hmm. In this case, D2 will be off or on when it is open. Yes. So you have to make assumption, right? You have to make assumption that so which one is off, which one is on. Yes. So when the switch is off, okay. When switch is on, what is the meaning of switch is on and switch is off? That we have to understand. Yes. Okay. Yes. So switch is on means it is closed like this. Okay. And if it is open means it is off. Okay. That you have to understand, because this is what we have to make observation, right? So when switch is on means it is closed. So D3 by observation is okay, right? Understood? So your B option is correct. Okay, for that moment. And when switch is open, okay, when switch will be open, so what will happen here is that you have to understand this. When switch is open, so this 2 ampere is flowing. Okay, and you have to make assumption also that between this, right, because you have got C and D. So you consider that, what you can consider here is that, let me take, suppose this is grounded here and this is open, right? You consider D1 is not conducting for the moment. Okay, if D1 is not conducting, so what is the current flowing through this? This will be 2 ampere, right? Okay, if D1 is not conducting means this will be 4 ampere. Okay, understood, everybody? And if this is 2 ampere, so what is current flowing through this? This is 2 ampere, right? Okay, if D1 is not conducting, then what will happen? D1 will not conduct, then your D2 and D3 is conducting. That you have to understand. Okay, means KCL is okay, right? There is no violation of KCL. That is very important to understand. Okay, this assumption you have to make, because from the option D1 is reverse bias, D2 and D3 is conducting, right? Then switch is off. Okay, suppose you consider D1 is conducting, okay, and D2 and D3 is off. Let me take this situation as well. Okay, so if both guys are off, suppose this is off and this is off, right? So this current is coming 2 ampere, right, and this is conducting. Okay, and so this 4 is coming 4 ampere here, and so there will be a violation of KCL. Okay, because this is 4 ampere. Okay, and this current, where it will go, right? Where it will, because this is open, right? So this 2 will go like this. Okay, and 4 is coming, right? So there will be a contradiction. Okay, that you have to understand. So D1 will not be on. Okay, D1 will not be on. So D1 will be off in this case. So option C will be correct. Okay. Yes. Understood. If you directly take this is grounded and this is 0 volt, okay, D2 is on. Okay, if you consider, so there will be a violation of KCL. So violation should not happen. So when switch S will be off, so always keep in mind you have to consider D1 is reverse bias so that D2 and D3 will conduct. Understood? So option for this question will be B and C. Yeah. This question, yes. This is how we have to make observation, right? So question number 59 is what, guys? You look at 59. What question says is that the Zener diode in the circuit has breakdown voltage of 5 volt. Okay. Zener diode has a breakdown of 5 volt. The current gain beta of the transistor is given as 99. Okay. In ECE paper, these kind of questions will never be asked. Okay. Only in electrical engineering and instrumentation, they still ask bipolar junction transistor. Okay. But in ECE, nowadays, these kind of questions, they are not asking. Understood? Okay. So they have mentioned beta and they have said that transistor is in active region means we can use IC equal to beta IB relation. Okay. And also they have connected Zener diode. Remember always, whenever Zener diode is connected, so you have to always check whether Zener diode is on or off. Okay. So suppose this is Zener diode. Okay. I mean, whether it is in breakdown or not, that's what I want to point out, right? Suppose the breakdown voltage is 5 volt. So if whatever voltage is across will be there, suppose V naught is there, it should be greater than 5 volt. Then only this Zener diode will be replaced by battery plus 5 volt. Okay. Otherwise, if voltage is less than 5 volt, so your Zener diode will not be in breakdown, and you have to replace it by open circuit. Okay. So this is in breakdown, not in breakdown. Okay, these are the two equivalent we must know before we start solving. So initially what we can do, see if you consider that Zener breakdown is on, right? So it will be not a good choice, okay, because it will complicate calculation. You see here, the Zener diode has a breakdown 5 volt and the current gain beta of the transistor is 99, right? Beta is 99 and ignore the base emitter voltage. The voltage drop here we have to ignore, right? This 0 volt you have to consider, okay? Or you can say voltage drop will be ignored, understand? So, and consider that this Zener diode is off, okay? You have to make assumption and we have to check also, okay? Assume that Zener diode is off, not in breakdown, right? Is not in breakdown, right? That you have to make assumption, and we have to also check whether this assumption is correct, then only answer will be correct. Okay, so what they are asking, the current through 20 ohm resistor or resistance in milliampere we have to find. Okay, so means we have to find the current through this guy. Okay, 20 ohm, right? 20 ohm. Yeah. Now you can apply what now? You know that if this is open, right? So let me draw the circuit. Okay, I will draw the circuit here properly. Okay, so you see this circuit I am drawing again. So this is collector, right? And this is the 10 ohm. And now I'm not considering that the Zener diode is present. Okay, it is open circuited, you can say. And this is plus minus 25 volt, right? Plus minus. Whatever current is flowing through 7K, that will be equal to what? IB. Okay, that will be equal to IB because Zener diode is not present. And across this, the voltage 0 volt is there because we have to neglect the voltage. Understood? And then what you can say? Whatever you can connect here one resistor. This is the situation. right? So this situation, this 20 will be what? 20 will be what, guys? 20 will be what? So what you can do now is, whatever current is flowing here, whatever current, the current will flow here is IE, as we know. This current will be IE, and the same current will flow through 20 ohm as well, because now earlier it was connected like this, right? It was connected like this. From here to here, we have now considered, we have made assumption that the Zener diode is not in breakdown. So we can replace it by, okay, so we can replace it by, uh, you know, open circuit, right? With that equivalent, right? So across this, the potential drop is IB into 7K, right? And across this, what is the potential drop? That is 10 IE, right? And across this also you can find, so you can apply 1K, K, let me apply it. You can apply 1K VL from here to here, right? So I'm just applying, so it is minus 25 volt, uh, you know minus 25 plus, it is IB times 7 kilo plus 10 times IE plus 20 times IE equal to 0. Okay, guys, this is fine for everybody. Understood. So you can take this 25 that side. So 25 equal to IB times 7K, right? Plus IE common, it will be 30. If I'm not wrong, right? So now what you can do, uh, that is fine. So this is 25. And how can you write IE in terms of IB? IE in terms of IB, yeah. So this is going to be 25 equal to IB, okay, 7K plus, what is IE in terms of IB? You know that. Suppose IE you know, so you can find IB. IB will be IE upon beta plus 1, right? Beta plus 1. So you can multiply here, so it will be IB times beta plus 1, that is 100 into 30. So 25 equal to what? It is IB 7K plus, it is 3000. So you can say 3K times IB, right? So you can add now. So this will be 10K IB, which is equal to 25. Okay. Now from here you can find IB. IB will be what? 25 by 10K. So it is very simple. Directly you can say this will be equal to 2.5 milliampere. So whatever current is flowing, see, whatever current is flowing, okay, whatever current is flowing through this 20, if Zener diode is not in breakdown, will be equal to IE only, right? So simply what you have to do, you can say IE will be equal to beta plus 1 times IB. So this is 2.5 milliampere into 100, because beta is given as 99. It will be 250 milliampere. Okay. Also, you have to verify whether our assumption is correct. So you can find the voltage drop across emitter resistor. Across this 10 ohm, right? So what is current? Current flowing is you can say 250 milliampere. Okay. So 250 milliampere times the uh, 10, it is approximately 2.5, right? The voltage across this will be 2.5, and it is connected across the Zener diode, right? So if this is Zener diode, right, and this is 5 volt, it has breakdown voltage of 5 volt, and if you are applying 2.5, this voltage is less than this voltage, right? So your Zener diode will not be in breakdown, okay? And if it is not in breakdown, you have to make it open. So your answer for this question will be what, guys? 250. Amit, you understood this now? First, what you have to do? You have to consider what? Zener diode is not in breakdown. Okay, if Zener diode is not in breakdown, means you have to replace it by open circuit. Okay, if it is in breakdown, you have to replace it by battery plus minus. Okay. So this question you can do easily, and the answer for this question is 250. Very good question. They have mentioned rounded off to two decimal. Needless to worry about that. Perfect. Next. Next question is again one of the very beautiful question you see asked. Okay, in this year. Okay, and it is very easy question. Right. So the question number 33 is here in the original paper. If you take. So if you read the question here, what is the question? The question says is that the diode in the circuit is ideal. Okay, they have given diode in the circuit is ideal, and the current IST equal to pi sine 300 pi t. Okay, milliampere, and you have to find the magnitude of the average current. Okay, you have to find magnitude of the average current. Right, magnitude of average current. This is very good question. Okay, try this. So what you can do here is uh, this is given as pi sine 3000 pi t. Okay, and this diode is connected here, right? So this is simple, kind of. Okay, there is no capacitor, only diode and resistor is there. So you have to, first of all, you have to determine. Okay, you have to determine what you have to determine that this is very simple circuit. Okay, let me draw as well. So we draw the circuit like this, and the current is flowing through this. Okay, sinusoidal current. Yeah. So you have to find the magnitude average current flowing through R. So you have to find current through this, right? I. Okay. Average current. So only single transistor is given, and this is so you can say kind of a rectification will be there. Okay. So for the positive half cycle, if you take positive half cycle, your diode will conduct. Okay, diode is conducting. So what will happen here is that this will be replaced by short circuit. Okay, as far as the diode is concerned, diode is ideal. Okay, if the diode is ideal, always keep in mind you have to replace it by short circuit. Okay, that is for sure. Okay. Hmm. So then what will happen? Then you can replace it by short circuit, so you will not get anything in the output. Understand? So yeah. But if you are in the negative half cycle, if you are in the negative half cycle, okay. So what will happen? So for positive half cycle, you will not get anything, right? Like this. But for negative half cycle, you will get something, So what is that? You will get the same you can say minus pi only. Yeah, but for positive half cycle you will not get anything, right? Suppose input is like this sinusoidal, so input is pi here and it is minus pi, right? Because for negative half cycle, okay, it will be open, your diode will be open, right? Your diode will be open, and then what you have to do, you can replace it by open circuit and current will not be there, right? Again for positive half cycle it will not be there like this. So it behaves like a half wave rectifier. Okay, and the V max you can say, or you can say I max is minus pi here. So what is average? I average for half wave rectifier is what? Im by pi. So Im is what? Im is minus pi upon pi. You can say minus 1. But what they are asking is, what they are asking. See, this is given in milliampere. Remember that. Okay, this is given in milliampere. So this will be answer. Okay, milliampere. Okay, in milliampere only. Okay. So understood. So you have to put the magnitude here. So answer will be 1 milliampere. Okay. So this question was very simple question. Amit, you have understood this now? See, again let me explain. If you are in positive half cycle, so this diode is conducting, so you have to replace it by short. If it is short, so voltage across the resistor will be zero, right? So zero current will flow. Yes. entire current will flow through this short circuit. Okay, no current will flow through R. Understood? No current will flow through R. Yes. And when you are in negative half cycle, so because of negative, as it is current, okay, because this I will be equal to Is only. So as it is, whatever input waveform is there, the output waveform, because this is ideal, voltage, sorry, this is ideal diode. So answer will be 1 because they are asking magnitude. Okay. Chalo. So question for, this was a question, very good question, right? So you try this. Again, question number 26. This question each year you will expect in EI, in instrumentation branch, right? If you're from instrumentation branch, this kind of question will be there, okay, based on non-ideal op amp. Okay, so this kind of question we have to always solve it. Okay, never ignore question based on non-ideal op amp. Okay. So can we read the question? The op amp is in the circuit shown is ideal. Okay, so basically they have told that op amp is ideal, perfect, except that there is some non-ideality. Okay, that's why they have mentioned except that. Okay. What is exception here? It has an input bias current of 1 nano ampere. Right? They have mentioned here that there is a current, input bias current. So this is the input bias current, 1 nano ampere. Okay, and input offset voltage is also mentioned. They have mentioned that there is an input offset voltage. How much input offset voltage is there? See, they have mentioned here is that input offset voltage. Okay, how much it is? That they have given 10 microvolt. Okay, so what you have to find, the resulting worst case output will be what? Plus minus microvolt. Okay, plus minus microvolt. Okay, so you see here they have said that these are the things which are grounded. So you have to consider that there is an input offset voltage. Okay, that is given as you can say VIO, which is given as what, 10 microvolt. Okay, there is a okay, and there is a current also through this terminal as well, that is base. Okay, now you can apply one KCL at this point. Okay, you can apply one KCL at this point. Now you don't have to consider, what is KCL at this point? Can somebody tell me? Yes. So you have to consider this potential here as well, right? So after all, they have given input offset voltage. So this is VIO. So you can apply KCL at this point. So this is the current coming, right? And this is current going and this is current going, you can say, right? So let me write KCL at this KCL at inverting terminal. Okay. So this will be 0 minus VIO upon 1K plus okay, VIO, or else what you can do, let me take yeah, or else you can write like this also, just change the direction of this. Okay, or else you take like this only. So 0 minus VIO upon 1K, and one current is coming and two currents are going. So you can say incoming equal to outgoing. So it will be VIO minus V naught by 100K, and this is 1 nano ampere, right? You can say IB is given. Understood, guys? This is okay. Now what you have to find out, you have to find out V naught. Okay, V naught you have to find out. Perfect. So you can further solve this. Okay, you can further solve this. Okay, because but as these values are different, you see 100K, 1K. So what you can do, you can consider this is R2 and this is R1, and you can solve easily. But it's okay. Let me further solve. It is minus VIO upon, because VIO you know already, so you can easily find out V naught. Okay. So it will be what? 1K equal to VIO by 100K minus V naught by 100K plus I and A, right? 1 nanoampere, sorry. 1 nanoampere, right? Simple, it is simple. You can just plug all the values, whatever values you have got, right? So what is, let me put here, so 10 microampere, so it is 10 microvolt, sorry. So this is 1K, okay, equal to, this is plus 10 micro upon 100K minus V naught by 100K, and this is 1 nano, okay. 1 nano means 1 into 10 raised to power minus 9, right? So though you should know the expression, you should know the expression directly, right? There is a expression, very popular expression for this question. If you know, then you can directly solve this. You know, you will, otherwise you might get lost in this mathematics. So whenever IB is given, okay, and offset voltage is also given, right? So output for this kind of transistor will be, as you can see, this kind of transistor will be what? IB times R2 plus 1 plus R2 by R1, R2 by R1 times input offset voltage, okay? Understood? So this, in this expression, you can easily put the value and you can get the answer. Otherwise, you can also solve this as well, okay, this equation. Understood? So yes, otherwise it will, what will happen, you can, if you take kilo cancel, if you take kilo cancel here, so you can take kilo common, right? So it will be very lengthy, but it's okay. We will directly put the value here because we have directly put the value here, right? So what you can do, let me remove from here. Either you can solve this or directly you can put the value on in this expression. So IB will be, IB is given as what? IB is given as, let me take this equation in the next page. Here only you can take, right? So 10, okay, 1 nano means 10 raised to power minus 9, and R2 is given as 100 into 10 raised to power 3 plus 1 plus R2 by R1 means this is 100 only into VIO, right? That is given as 10 into 10 raised to power minus 6. Okay, so when you will solve this now, you will get around 111, 0 microampere, right? So not microampere, it will be in volt. So when you will solve this, you will get 1110 because you have to answer in microvolt. So answer for this question will be 1110. Now you may ask, sir, how you have got that expression, right? How we have got that expression? So answer you have to put in this, okay, 1110 microvolt. So how do I get that expression? That you have to keep in mind. So what you can do, replace this 1K, whatever we have considered here, this is R1 and this is R2, okay, and this is IB, and solve this, right? So you will get this expression directly, right? What we have done, we have directly taken these 100K, 1K, and we are getting messed up, right? And if you will solve this, you will get this only, 1110. So answer for this question will be 1110. So remember, whenever input bias current is given as well as offset is also given, okay, so what you can do, you can directly use this expression, right, and write it, okay. Consider that this input offset voltage is given here, okay, in the non-vertic terminal, and you can do it, okay. So answer will be that. And I believe this is the last question of the day, but still we have got two questions, right? Yeah, so two questions we will do here. The question number 60, it is one of the very good question. Okay, this year was asked in instrumentation branch. So this is okay, and yeah. So in the circuit shown, the input voltage Vin is given, that is 100 millivolt. The switch and the op amps are ideal. Okay, the switch and op amps are ideal. At time t equal to 0, the initial charge stored in the 10 nanofarad capacitor is this. So they have mentioned 1 nano capacity, 1 nano coulomb charge is also present, that is initial charge, with the polarity indicated in the figure. Okay, this 10 nanofarad. Okay, so minus to plus. The switch S is controlled using 1 kilohertz square wave voltage signal Vs as shown. Whenever Vs is high, the switch is in the position 1, in the position 1. See, whenever this is high, your capacitor will charge. And Vs is low, when Vs is low, right? When Vs is low, S is in the position 2, right? Means it is here, right? So you have to always keep in mind that when this switch is at position 1, so this 1 nanofarad capacitor will charge, okay? And when it will be low, so this will be connected to this, okay? So you have to go for op-amp circuit, right? So let us analyze this circuit. This circuit is one of the very good circuit, and one of the very good question, in fact, you can say, right? I believe you guys might have seen, okay? So whenever they have mentioned the frequency, right? So this waveform they have mentioned, so you can find the time period as well. The time period for this waveform will be what? The time period will be 1 upon 1 kilo. That is 1 millisecond. 1 millisecond will be the time period for this waveform. Right? And whatever in the question they are saying, we have to follow that simply. Okay. So initially they have given that the charge is 1 nano coulomb across this 10 nanofarad. So we have to consider the circuit. Okay. What is the circuit here? Okay. What is the circuit here? 1 minute. Yeah. So for t less than 0, if I see the circuit, okay, for t less than 0, your charge is stored in the C2. Okay, you can say charge stored in, you can consider this is C2, okay, and this is C1. Okay. Charge stored in C2 or is what? 1 nano coulomb, right? Hmm? That you have to consider. If there is a charge, so you can find Vc2 as well. So Vc2 will be what? Q times C2. Q times C2, which is going to be 1 nano coulomb upon 10 nano farad. Right? So this will be 0.1 volt. Okay. So the moment you have been given initial charge, so you can also find the initial voltage, right? Okay. I believe this is fine for everybody. According to the given polarity, what will be Vc2? It will be minus. Okay. Okay. Minus of, understood everyone? It will be minus of this 0.1. Understood? And we have already calculated the T naught. T naught will be 1 upon F naught. That is, you can say 1 millisecond. This is the time period you can evaluate directly. Understood? Now we have to go for the pulse. See, this is a pulse they have given. So high, okay. Then you can say like this, okay. So one time period is T naught. So this will be T naught by 2, okay. And this is 0, you can say, and this is okay. Let me get back to the circuit. This, yeah, high and low. Okay, so high voltage and low voltage, right? High voltage and low voltage. Okay, so initially it is high voltage, and the V input is given as what? V input is given as 100 milli. Okay, so high voltage means 100 milli. Perfect. So if this is 1 millisecond, so this will be 0.5 millisecond. So for high means you have to be between, for t between 0 greater than 0 and less than 0.5 millisecond, right? This is the time we have to check. Okay, so when you are in between 0 and input is applied here, which is high, okay, So what they are mentioning here is that when the switch S is controlled using 1 kilohertz, okay, square, okay, whenever Vs is high, okay, whenever Vs is high, so S is in position 1, okay. So your C1, the 1 nano capacitor, 1 nanofarad capacitor will be connected with this. So this will charge, you can say, right? So you can say C1 equal to 1 nanofarad will be charged. It will be charged, okay, up to what? Up to 100 millivolt, right? Up to 100 millivolt, it will be charged directly. Now come to this. So for, okay, because switch is connected to what? Your input is connected to, Vin is connected, okay, connected to C1, right? That you have to understand. Okay. Next, for time, if you take for time, okay, according to this, between 0.5 millisecond to 1 millisecond, okay, your input is low, okay, your input is low, right? So now this C1, okay, this switch will be connected to what? This switch will be connected to this, okay, and input is not connected now, okay. That you have to keep in mind, okay. So your circuit is like this, plus minus 1 nanofarad. This is here. This is minus plus, and this is V naught, right? Minus plus. Okay, because your switch is now connected to the position 2. Okay. So for time greater than 0.5 millisecond to less than 1 millisecond. Okay. Your capacitor 1 nanofarad is connected to inverting terminal, right? This is connected to inverting terminal. This is the inverting terminal. Okay. So what will happen if it is connected to inverting a terminal? Okay. So you can consider here the potential, some potential you can consider. Already you know that the voltage across 10 nanofarad is 0.1, right? Already you know this, okay? So the moment this will connect to this, okay, so it will start discharging as well, because current will flow like this. In the beginning, current was flowing like this, okay? So your 1 nanofarad capacitor was charging. Now it will discharge, okay? Your C1 will discharge, okay, or you can say 1 nanofarad capacitor will discharge, okay, instantly discharges to 0, right? You can say. So this capacitor will discharge, right? Okay, understood? Because current will flow like this, so current will be flowing like this, okay. So let me draw the circuit here. Uh, Situation is like this, okay. Here, this is capacitor, okay, and you can take this as C1 and this is C2. Okay, so this is C2, this is 1 nanofarad, and this is 10 nanofarad. Okay, and the polarities you have to take care. Whenever current flows through the capacitor, like from minus to plus, you should know that capacitor will discharge. Okay, and one of the terminal of the op amp, as you know that one of the terminal of the op amp is 0 volt here, so it will be 0 volt, right? So initially, what will happen? This capacitor will discharge, okay, to the 0, you can say, because there is a 0 volt. Otherwise, if it is not discharged, then there will be a problem. Okay, that you have to understand. Huh? So because op amp is ideal as well. Understand? Okay. So now what you can do? So your C1, okay, will discharge to 0. So what will be the change in voltage across Vc1? You can say voltage across C1 or voltage across 1 nanofarad will be, initially it was 100 millivolt. Now it is 0, right? So change is this. Okay? Change is gonna be this, right? Okay, change will be like this, and this current will flow like this. Okay, remember always this current will flow. So this C1 will be discharging through this C2, right? That you have to keep in mind. Okay, because current cannot go into the op amp, that you have to understand. Okay, and then what will happen? So you remember always this 1 nanofarad capacitor will discharge to 10 nanofarad capacitor. Understood? Huh. So you should know one of the very important concept here we have to use by charge conservation. Okay, by charge conservation. What charge conservation said that charge lost by C1 or 1 nanofarad, right? Charge lost by 1 nanofarad will be equal to charge supplied. Okay, charge supplied to 10 nanofarad. Okay, that you have to keep in mind. So what is charge basically? C1, or you can say 1 nanofarad into change in voltage. What is change in voltage, guys? This is 100 millivolt equal to C2 means 10 nanofarad, and what is change in C2? We know already, right? Change in C2 is what? Okay, you can find out C2 change in C2, because here we know VC2 but we don't know change, right? That is change in VC2 we don't know. We can find change in VC2, which is going to be uh, you can solve this, so it will be 1 nanofarad upon 10 nanofarad. Okay, nanofarad will get cancelled, it is 100 millivolt and 0 0, so it will be equal to 0.01 volt. Okay, I believe this is fine for everybody. Okay, so you have got change in VC2. See, in one cycle your voltage across 10 nanofarad changes to what? 0.01 volt, right? You have to write here. Okay, in one cycle, you see. Okay, in one cycle, why we are saying? Because see, this is the total time period, and we were at 0 to 0.5. So your 1 nanofarad capacitor was charging. Okay, because this switch was at, okay, first position. Now when you are between 0.5 and 1 nano, 1 millisecond, so your switch is at two positions. So this C1 will discharge, you can say 1 nanofarad will discharge this through C2. Initially this voltage was 0.1, now it has become 0. Understood? So this is very important concept. So in one cycle, voltage, okay, voltage across C2 charges to 0.01 volt. Okay, so at 20 millisecond, what will be happen? Okay, at 20 millisecond, you see what they are asking in the question. You see, at 20 millisecond, the magnitude of the V naught. Okay, this is very important question. Okay, see, in 1 millisecond, okay, in 1 millisecond, the VC2 changes to what? There is a change in VC2, that is 0.01. Amit, are you understanding this point now? Okay, at 1 millisecond, you have to start analyzing from the very beginning. Okay, because in the question they are asking at 20 millisecond, means you have to multiply by 20, है ना? So you have to multiply by 20. Okay, so 20 millisecond. See, voltage across C2 changes to this should be changes, not charges. Okay, changes to 0.01. Okay, so now at 20 millisecond, what will happen? You have to multiply by 20. So it will be, you can write change in Vc2 will be 20 into 0.01, that is 0.2 volt. Okay, I'm talking about at 20 millisecond, right? At 20 millisecond. Okay, now what you can do, you can now find Vc2 at 20 millisecond, because they are asking Vc2 at 20 millisecond. So this is change in Vc2, remember. Okay, so we have to find, I'm just writing here now. Okay, so Vc2 at t equal to 20 millisecond will be what? Vc2 at t equal to 20 nanoseconds. So initially, what was the voltage across capacitor at t equal to 0 millisecond plus change? Okay, so Vc2 was minus 0.1, now it is 0.2. Okay, what you are getting here is, you will get 0.1 volt. You are getting 0.1 volt. Understood? This is the voltage across the capacitor, Vc2, right? So what they are asking now, because now you have already find out that 0.1 is the voltage across the capacitor, right? But you have to understand that what is the voltage, you have to find the output voltage here. Don't forget that. Okay, that is very good question. Okay, so what you can do, you can apply one KVL like this. Okay, so voltage across this is 0, right? Just apply one KVL, right? So what here 0 volt you consider, right? So V naught will be equal to, what? Minus Vc2, right? So your answer, so here your V naught will be equal to minus Vc2, which is going to be minus 0.1 volt. Okay, now minus 0.1, but what they are asking, they are asking the magnitude of the V naught. Okay, so they are not asking the voltage across the capacitor at 20 milliseconds. This is very important to remember. Okay, what they are asking is at 20 milliseconds the magnitude of the voltage V naught. Okay, so this is very important to remember, and this polarity you have to take care, right? So minus, okay, if you're taking first sign here, plus V naught minus Vc2 plus V naught equal to 0. Okay, so from here, what you're getting here is, I think you're getting only, uh, you know, perfect. Yeah. So, okay, perfect. So, in the circuit already they have mentioned this now. So, yeah, it is direct. Okay, so you can directly find out. So, it will be 0.1. So, answer will be for this question. But you have to answer in millivolt also. You have to take care. Sorry, right? So answer will not be 0.1, because 0.1 can be written as, okay. You see, guys, this is very important to be very careful, right? Okay, as we have got Vc2. Okay, Vc2 is what? Minus 0.1 plus 0.2. This is 0.1 volt. Okay, now we are getting V naught equal to uh, minus 0.1 volt. Okay, so minus 0.1 volt means what? In milli, what will be there? Can you, Amit, tell me? 0.1 will be in milli, how much? So it will be 100 millivolt. Yes, 100 millivolt. Yes, so it is in minus if you take. So you have to put the magnitude. Needless to worry about sign here, because they are asking magnitude, so it will be the answer as 100. So this question was one of the very good question. In fact, we will again discuss in the classroom, right? Again, we will see, okay, okay, so there should not be any calculation mistake. We have to analyze this question properly, okay, and we will take other solution also, but this concept is very important. Okay, whenever charges are given, you have to apply the charge conservation. Next, the question number last, okay, this is a question, okay. You see there are Gina diode again connected and normal diodes are there. So consider that the op-amp based circuit shown in the figure. Ignore the conduction drop of diode D1 and D2. All the components are ideal, and breakdown of the zener is 5 volt. Okay, that we have to understand. Uh, and they have given that which of the following statement is true. Okay, so they have given some supplies as well, minus 15 to plus 15. Okay, and yes, so during positive half cycle, okay, as there is nothing like positive feedback and all, so during positive half cycle what will happen? During positive half cycle, this potential, okay, during positive half cycle, okay, this potential will be you can say negative, right? This potential will be negative, so here minus 15 volt, right? Because you can think like that, but it is not the case, okay, because this is not the comparator circuit, right? As I can see, it is minus to plus. Okay, so what you have to find, first of all you have to check the maximum and minimum voltage, minimum value of the output voltage V naught are plus 15 and minus 10. Okay, so you see this circuit, guys, and we have to solve this question, right? So we have got Gina diode as well. So during positive half cycle, uh, this diode will conduct, this diode will not conduct. Okay, this diode will certainly conduct. Okay, D1 will conduct, but D2 will not conduct, and D1 and D2 are ideal, you can say. Okay, and this breakdown voltage is also given, right? So yeah, so it will not be in breakdown also, this will not be in breakdown. So initially what will happen, the whenever for the positive half cycle, you can say the output will be what? Output will be V naught equal to minus R2 by R1 times V in, right? So this is 1k 1k, right, and this is 10. So the answer will be, maximum will be 10, right? Here they have mentioned maximum is 15, that is wrong. Okay. So maximum should be 10, right? Maximum should be 10. It should be wrong also. It is also wrong. Okay. So in which option maximum is present? Maximum will be 10. Okay, because this diode will not conduct. Okay, while you are in positive half cycle. If this is positive, so we always consider this should be negative. Okay, output will be negative. Okay, so this diode will not conduct, this will not conduct. Okay, so this is going to be conducting only D1, so maximum will be that. And when you are in negative half cycle, so your Gina diode will be can be in the breakdown as well. You have to check, yeah, it will be in breakdown because this is 10. Okay, and this D1 will be off. Okay, so you can replace it by open circuit. Understood? So let me check the exact answer key what is given. Okay, so we can finalize the answer. So according to you, which option is correct? Yes, guys. Because maximum will be 10 volt only. Okay. Yes. Okay. In this question, what we have to do, like I told you now, see, I'm taking based on input, right? Input is maximum is 10. Okay, maximum is gonna be 10, right? V max is 10, V minimum will be minus 10. Okay, but we have to find the answer for V out, whether V out will be maximum or minimum, right? Okay, so by looking at that, what we were trying, okay, what we were trying, the answer is coming out. to be option C, right? But what is the reasoning here? How we are claiming that this Zener diode is off, right? That's what we have to check. Because until you check Zener diode is off or on, we can't answer directly that option. Okay. So we have to find, remember, we have to find V out minimum and V out max. We can't answer directly that option C is correct and okay, like that initially. Okay, we have to find V out. Okay, so if Vi is, suppose Vi max is what? Vi max is 10 volt initially, right? So your D1 will be on and D2 will be off. Okay, so output will be what? Output will be equal to minus VEI. Okay, and minus Vi is minimum, guys. Okay, this is the concept we have to think about it, right? Output you are getting is minus 10. Okay, okay, because already I have told you that 1k upon minus of 1k upon 1k into V, right? So this is minimum voltage you are getting. Understood? If it is okay, uh, Amit, now you understood now? Yeah. So there should be minus 10, right? So V naught minimum will be minus 10. I think in only one option it is present, right? Here nothing is, okay, this is also present. So option B and C is neglected. Option D can be correct and option A can be correct. Now we have to check. So this should not be correct because there is a maximum voltage plus 15. Okay. If plus 15 will be there, then it will be saturated. Okay. So output cannot be equal to plus 15 or nearly that. So option should be D is the correct answer here. Okay, Amit. Now you understood what I am trying to say. See, when you will take V max, okay, so you have to you have to think that when D1 is off, suppose when D1 is off, okay, so this should be on. Right? Your Zener diode will be on, okay, and this will be replaced by short circuit. Situation will be like this: minus plus 5 volt, and this is input, you can say. Okay, so your maximum output will be what? Your Vi max is basically 10 only, and you have to consider the, okay, V naught. So V naught, you can directly say that 5 volt will be the V naught. Okay, when Zener diode is on. Okay, yeah. So when Zener diode is on, so maximum you will get is, okay, 5 volt, and that too you have to understand. Okay, so this question is very easy question, provided you have to you can't answer directly that minus 10 is the correct answer, right? Because minus 10 will be minimum only, it will not be maximum, right? But here plus 10 is given, that is, so option D is the right choice. Okay, so guys, thank you so much. What we will do here is, we have discussed many concepts. Okay, there are few questions which are very good in instrumentation. Okay, we will conduct again. Okay, we will conduct again few sessions. Okay, we will catch up. Okay, and we will study all these things in the classroom also. So you can follow us on Facebook and Instagram, everywhere, right? On Telegram also we have one of the dedicated group. Okay, and you can also subscribe our YouTube channel where you will get all the notification related to all these things, right? So there were few questions which were very good. Okay, so we will again solve them in the classroom, regular classroom. Okay, and in the less time we have done these many questions. So this question was very good question. Okay, again you can revisit this question and think about this. Okay, so thank you so much, guys. We'll catch up next time. Thank you.